All right, there we go. All right, so the topic today is photoelectron spectroscopy. And we use this in AP Chem quite a bit. And just kind of a background to it. We talked back in chapter 5 about when you shine light on a metal, if that energy is strong enough, it can eject an electron away, okay, if it's the right frequency. And so that's known as the photoelectro effect. And what they do with this photoelectron spectroscopy is they take advantage of those electrons that are popping off, and they look to see what kind of energy is required to make that happen. So they're using light, and that's where the photo comes from, to eject a electron away and then measure the energy that's needed. So this is kind of a diagram of what that looks like, where you have light coming in. If that frequency of light carries enough energy, that it's going to cause these electrons to pop off, and they can measure those electrons and how much energy is required to make that happen. So there's what's called a threshold energy. So if you're thinking about like a wave, if you've got too low of a wave, it's not going to cause the electrons to kind of pop off. But if you get that wave going high enough, it's going to cause those electrons to move. So you can think of those frequencies as kind of a threshold amount, and that's where they have the O here is the threshold, the minimum amount of energy that's required to cause that electron to pop off. So if we look here, like with this red light, it wouldn't have enough energy to make that happen. The green light is just hitting that threshold energy. It's just enough to make those electrons pop. And then these are making the electrons just boom, go right out of there because it's got a lot more energy. And we talked about how blue light had more energy than red light when we were back in chapter 5. So they looked at that. They saw that if we have a certain amount of energy, that we can eject these electrons, and that minimum frequency is called the threshold frequency. And for frequencies greater than that, of course, they're going to cause that metal to um, move those electrons off. So the more kinetic energy the photoelectrons have, it's proportional to the light frequency. So what they're saying is the frequency of light comes in, you can measure the energy of these electrons. The higher the frequency, the more energy, the more kinetic energy these electrons are going to move with. So this kind of shows you that relationship between the kinetic energy and the electron energy here. So the light frequency is the energy, as the frequency increases as we move across here, so does the kinetic energy. And then that electron current, though, is going to stay the same. So it doesn't matter whatever current is caused by those electrons moving, it doesn't matter how high that frequency is, it's still going to give you the same current. It's still going to give those electrons are still going to give you the same amount of current through there. Why is this not moving? Okay, here we go. All right, so if we go back, remember this guy, we could figure out the energy of a photon. Back in chapter 5, we did this. This was Planck's constant. This was the frequency. And if we multiply those two things together, they give us the energy of our photon. So we could look at that in terms of, okay, how much energy is that photon going to give? This is how we would calculate that. So the photon, and then if you know the threshold energy, what that energy has to be in order to eject the photon away, then you will be able to see, oh, yeah, this photon has more energy than this one. Now, don't look at the first numbers, okay? Look at these. This is a bigger number than this number, okay? So don't let the front numbers confuse you. You got to look at the whole picture here. So this is the threshold energy that you need. This is greater than that. That means that that's going to eject a photon. Okay. And we can go through all the calculations of that. We can see that there's enough energy there that we have a positive difference, which means that we're going to eject it. So what they did was they looked at a wave model of light and they increased that light amplitude and they saw that the kinetic energy is going to increase. And then they were able to use this equation to determine the energy that's by a certain light. And then if they know the threshold energy, they'll be able to figure out if that's going to eject a photon. So what they did was then they came up with a device called a spectroscopy device, and they were able to measure these photoelectrons and how much energy that they are creating when they eject the electrons. There's different types of photon spectroscopy, but essentially what it boils down to is they're measuring the energy that's needed to be able to eject those electrons. So, if we look at like lithium, for example, and we look at the energy that is binding or holding that electron onto a lithium atom, we can see how much energy it's going to take to pull that first electron away. And that energy that's holding those electrons in place is called binding energy. It's binding that electron to that atom. So we can do that for a couple different electrons in our lithium. So the first electron here. Now, let me caution you about these graphs. Okay. Sometimes the graphs are set up with the lower number here and the higher number here. Other times they're set up opposite. You have the bigger number here and the lower number here. So you always have to look at your Y or your X axis to see how it's set up. Okay. So this is a greater amount of energy. That means that on this graph that your nucleus is going to be over here. Okay. And then you're going to have levels coming off of that. So wherever your bigger number is here, that means that you're closer to the nucleus. And if you think about that, that makes sense. This electron is not going to be held as tightly as the electrons that are closer to the nucleus. Because remember, as distance increases, what happens to your force? It decreases. So it's going to take less energy to pull this electron away than it would take these electrons. And what you can do is you can count your electrons. If they didn't tell us that this was lithium, we could count our electrons and we could figure out what element this is. And that's exactly what these PES uh, values do. They're trying to determine what elements are composing a particular sample. So for here, if we look at this, you can tell that the height of this is approximately twice the height of this. So you've got 2 electrons here and you have 1 electron here. So that makes up how many electrons in this atom? 3. And number 3 on the periodic table is lithium. You can also get your electron configuration from this as well. So this ends up being 1s2, 2s1, and that is lithium's electron configuration. Okay, so that's essentially what I went through on this slide. Now here is oxygen. Oxygen, we didn't have enough room to fit this all in like one fell swoop here, so they broke this up. So you've got oxygen, you've got this, and then imagine this graph right here is coming down here and continuing on. Does that make sense? Okay. So which electrons are closest to the nucleus? Electrons 1, or I should label these A. so we don't get confused. B or C? Which ones are closest to the nucleus? I heard A and I heard C. Anybody want to argue C? Nope. Okay. Well, like I said, you're going to look and see where your values are the greatest. My value is the greatest here, which means that my nucleus is here. Yes, there we go. Okay. And these then are going to be my 1s2 electrons. These and these then are going to be further away from the nucleus. Which ones are going to be closest to the nucleus, B or C, in this grouping? C, because my energy is greater here. So these are closest to my nucleus. So those are my 2s2. And then these are going to be my 2p4. Okay. So you add up, you can also add up those electrons then. You've got 2, 4, that's 6, 7, 8. That's going to tell you that it's oxygen. All right, so see if you can figure out, or did they tell us on here? Maybe they told us already. Yeah. So again, these are closest to the nucleus because my values are the highest. Remember, those are going to be the hardest electrons to pull away. Okay. So this is my 1s2. This is my 2s2. These are going to be my 2p6, 3s2, and 3p1. So also notice that there's some gaps here in our values between, like here it's 151 and then we jump down to 12.1. Why is it so much harder to pull these electrons away than these electrons? It's the same amount of them. Right. These are closest to the nucleus, so that force is going to be greater here, holding them in place than these. Also, by the time you're trying to pull these two away, you've already pulled all of these. They're gone. Okay. So you've got 13 protons pulling on 2 electrons. That's going to be really, really hard. You're close and you've got a significant effective nuclear charge pulling on those electrons. So it's going to just make it even harder. All right. Oh, does that make sense as far as how you read those PES graphs? Okay. So then you've got some homework on that. And then we'll talk about due dates and that sort of thing in just a second. Let me stop this recording.